In the last lecture, we started talking about bivariate transformations, and today we're going to continue and do a bunch of examples of bivariate transformations. So last time we had left off with an example of a continuous bivariate transformation, and that transformation was we transform some variables, random variables x and y, into u, that was x plus y, and v, that was x minus y. And we had said that, and we had derived, using the theorem, kind of our bivariate continuous transformation theorem, that if we looked at the joint PDF of u and v at little u, little v, this was the joint PDF of x and y at u plus v over 2, comma, u minus v over 2, times 1/2. And this we derived last time, so you can go back to the end of that lecture and look at how we got that. And we had derived this kind of generally without reference to what the random variables x and y were. So let's look at some examples of this. So for example, we could assume that x and y are distributed following a standard normal distribution. And I'm going to write this as in our kind of typical way, but I'm going to add the string IID over our tilde symbol here. And that stands for independent and identically distributed. And identically distributed. So normally I would say, for example, x is distributed following a normal 1, 0, 1 distribution, or y is distributed following a normal 0, 1 distribution. Here I'm saying x and y are independent and identically distributed following a normal 0, 1 distribution. And what this means is that x follows a normal 0, 1 distribution, y follows a normal 0, 1 distribution, and x is independent of y. So this is some shorthand notation that we'll use and is going to be very commonly used throughout probability and statistics. So if x and y are IID, normal 0, 1, then we can look at the joint PDF of x and y. If they're independent, this is the marginal PDF of x times the marginal PDF of y. And since they're standard normal 0, 1, we know what those are. The PDF, the marginal PDF of x is 1 over 2 pi e to the negative 1/2 x squared. And the marginal PDF of y is similar, but replacing x with y. And those are the PDFs of a standard normal distribution. And so according to our formula then, if we wanted to transform x and y into x plus y and x minus y, all we would do is take this joint PDF. So let's kind of bring this down here. We would say that f of u and v is, well, we're just going to take this joint PDF and we're going to plug in u plus v in place of x, and u plus v over 2 in place of x, and u minus v over 2 in place of y, and then we'll multiply by 1/2. So let's look at how that shakes out. 1 over root 2 pi e to the negative 1/2. And instead of x here, I'm going to replace it with, what do we have? U plus v over 2. Let's write that. And I have another 1 over root 2 pi. And I'm going to replace y with u minus v over 2. Whoops, I need my squares there. And then I have my 1/2, so I'm going to multiply by 1/2. So one could stop there. That would be correct if the question was just what's the joint PDF of u and v. That would be the correct answer. But in most of the examples we're going to look at today, you can kind of take it one step further and you can get some kind of nice results. So first of all, let's consider u plus v over 2 squared plus u minus v over 2 squared. If we square this out, this will be well, u plus v over 2 squared is 1/2. I'm sorry, it's one, well, we can pull it to 1/4, right? 1/2 squared is 1/4. And then we get u squared plus 2uv minus v squared. We get another fourth, and then we get u squared minus 2uv plus v squared. And if we were to add those together, we would get 1/2 u squared plus v squared. Why, and I pointed this out, well, we can combine the exponents in these two exponential functions here. So this thing can be written, sort of write it kind of a funny way. First of all, I'm going to break up that 1/2 into 1/√2 times 1/√2. So I could write this as 1/square root of 2 pi times 2. And then I'd have another one of those somewhere out here, square root of 2 pi times 2. All right, so that takes care of that 1/2. And I can break up this exponent into two exponents. So I could combine them into u squared plus v squared, and then break it up again, right? So, well, let me just write this all out for you. Let's say there'd be a negative 1/2, and then I'm going to combine my exponents, and that would be 1/2 u squared plus v squared. Okay, that is a little weird of a way to write it, but notice that I can then break this exponent up again. So I would get 2 pi by 2 e to the negative 1/2 times 1/2 u squared, and then I'd get a 2 pi times 2 all square root in the basement, e to the negative 1/2 times 1/2 v squared. So this is all just algebra to rearrange this joint PDF, which we derived above. But what you'll see here now, what you'll see when I point out, is that each of these are a normal 0-2 distribution. So if the variance were 2, then these would be normal 0-2 distributions. Furthermore, we have a function, say h of x, that is just, h of u, that is just a function of u, and let's say g of v, that is just a function of v. And so what this means is that u is independent of v, and surely u and v both follow a normal 0-2 distribution. Because they're marginals, I've basically separated it out into the two marginal PDFs. So the recap on this example, kind of a theorem we've proved, is that if I have x and y that are IID normal 0-1, then x plus or minus y is IID normal 0-2. That is x plus y and x minus y, or u and v, are independent, and they are identically distributed following a normal 0-2. So that's a cute little example. You can actually generalize this into a more general theorem. And the more general theorem is that if x and y are independent, and x has a normal mu sigma squared distribution, and y has a normal, let's say lambda tau squared distribution, so different mean, different variance, whatever symbols you want, then you can generalize this theorem. I'm not going to go through and prove it, but you could think about how you would modify the previous example there to prove this. That x plus or minus y are independent. So x plus y and x minus y are independent, and kind of x plus or minus y are distributed as mu plus or minus lambda sigma squared plus tau squared. Notice that it's not plus or minus tau squared. Our variance can never be negative. So even in the case where I subtract things, I still add the variances. I can subtract the mean, So the mean is the difference plus or minus the two means, but the variance is always additive. And that goes back to this example here, right? It's not like when I look at x minus y, I get a normal 0, 0 distribution. No, I get a normal 0, 2, so I still add those variances. And this could be kind of proved in a similar way to the example we just did. So another theorem that we should talk about at this point when we're talking about transformations is what happens is kind of how transformations and independence interplay. So independence and transformations. Okay. So if I have two random variables, x and y, and they're independent of each other, and g and h are functions that are just real valued functions, r to r, and u is g of x, and v is h of y. So what this really means is that u is a function of x only, and v is a function of y only. Then the maybe not too surprising but nice result is that u is independent of v. That is, if x and y are independent, and u is a function of only x, and v is a function of only y, then u and v, transformations of x and y, are also independent. So kind of individual functions of independent random variables are also independent. You could look at some examples. For example, if u is x squared and v is negative log y, for example, then if x is independent of y, u is independent of v. Pick your favorite functions is true for all functions. And this is a theorem that we can actually do a nice little proof of. It's just a couple equalities, so it's a nice example of a proof here. So let's write down the proof. So let's look at the joint CDF of u and v. We haven't looked at those in a while. The joint CDF of u and v would be the probability that u is less than or equal to little u and v is less than or equal to little v. And recall that in our example, u is, well, what do we say? U is g of x and v is h of y, right? So the probability that u is less than or equal to little u is the same thing as saying g of x is less than or equal to little u, and v being less than or equal to little v is the same thing as saying h of y is less than or equal to little v. And we could write this in terms of inverse images. This is the probability that x is in the inverse image of g of the set. Let's write it like this, negative infinity to u, and that y is in the inverse image of h of the set negative infinity to v. So those are kind of equivalent statements based on what it means for transformations of random variables. And so that's nice. If we have that x is independent of y, then we can break these apart. Statements about x and y can kind of be factored apart in this way, right? So I can just break apart the previous statement of a probability statement of x times a probability statement of y, based on the fact that that is what it means for random variables to be independent. And then I just basically undo my inverse images. This is the probability that g of x is less than or equal to little u, and the probability that h of y is less than or equal to little v. or the probability that u less than little u times the probability that v less than or equal to little v, which is fu of little u times fv little v. So what have I shown here? I have shown that I can take my joint CDF of u and v, and basically just through some definitional steps and then one use of the fact that they're independent of each other, and basically kind of write it in terms of x and y. Well, x and y are independent. Okay, I can break them up and then rewrite it in terms of u and v, and I get to the point where this joint CDF of u and v is factored as the marginal CDF of u times the marginal CDF of v, and this shows that u is independent of v, right? And that is kind of a theorem we had. If you can either factor either the joint CDF or joint PMF or PDF, then random variables are independent, and u and v are independent because I can factor that joint CDF. And the reason I can factor it is because x and y themselves are independent. Okay. So that's a really nice little theorem. It tells you that you can do what you want to do, which is that if things are independent and you're just looking at functions of just one or the other, you can also treat them as independent, and nothing bad's going to happen there. Okay. So let us continue on. Let's look at some more examples. So today's lecture is just a bunch of examples of bivariate transformations. So here's another example. Let's say that x has a beta distribution with two parameters, alpha and beta, and y also has a beta distribution with two parameters, alpha plus beta and gamma. And let's assume that x is independent of y. This is a bit of a contrived example, but nonetheless, we can look. If I were to ask you and say, consider transformation of these, where u is the product x and y, and v is just x, I could say, what is the joint PDF of u and v? So it might be good if you could pause it here and you could try and do the problem. And then you could watch and we could talk about how I would approach this problem. So here's how I would approach the problem here. First of all, we should notice that x and y are both bigger than or equal to 0. So they're positive. And this means that, in fact, they're not just positive. We can say even more than that, right? Is that beta random variables are constrained to be in the unit interval. So they're both actually between 0 and 1. They're positive, nice, and they're between 0 and 1. So generally, we have the fact that u is always going to be bigger than v, but they're going to be between 0 and 1, right? v is x, which is between 0 and 1. I'm going to multiply by y, which is another number between 0 and 1. So that will actually make that smaller. Oh, did I write this backwards? Yes, I did. I wrote that backwards. Let's back up here. u is going to be smaller, typically, than v, right? Because I'm taking v, x, and I'm multiplying by some number between 0 and 1. So there's this nice relationship that we should keep in mind, which is that you should always kind of think about how the random variables are related here. And so to get the inverse transformation, which is kind of always what we want to do, right? You get the inverse, you take some derivatives of it, and then it's pretty straightforward from there. So, I have these two equations, u is xy, and v is x, and I want to solve back for x and y. Well, solving back for x is easy. X is just v. And solving for y here, I could say it's u over x is y, which of course is u over v. So this would tell me that y is u over v. So those are kind of inverse functions, right? You could give them fancier names. X, which is, let's call it g1 inverse of uv, is just v. And y, which should be g2 inverse of uv, is u over v. So once I've got the inverse transformation, so g is my transformation, and with component functions g1 and g2, g1 and g2 inverse are the kind of components of my inverse transformation. What I need next is absolute value of the determinant of the Jacobian matrix. So let's look at what the Jacobian is, right? So as a reminder, the Jacobian is the matrix of partial derivatives of the various component functions. And in this case, we're calling J here, Jacobian. It's actually the Jacobian of the inverse. It's the derivative of the inverse with respect to u and v. So on the first row, it's derivative of the first component function with respect to u, then derivative of g1 inverse with respect to v, and the second row is derivative g2 inverse with respect to u, and derivative of g2 inverse with respect to v. And this is actually not too bad. The first row is just 0, 1, right? That's derivative with respect to u is 0, with respect to v is 1, of that boy. And then if we look at this other one, derivative with respect to u is 1 over v, and derivative with respect to v is negative u over v squared. And so if I look at the determinant of this Jacobian matrix, should just give me 1 over v, and the absolute value of the determinant is also just 1 over v, because v is positive. V is what do we say that this thing is? V is just x, and x is a beta is positive, so the absolute value is also positive. So that's kind of half the battle there. Once we get that, what we need to do is we need to plug in, if I want the joint PDF of u and v, I take the joint PDF of x and y, I plug in g1 inverse of u, g1 inverse of uv, g2 inverse of uv, and then I multiply by absolute value of the determinant of the Jacobian. So what I need here, so this is what ultimately we're going to plug in, what I need is I need to get this this joint distribution of x and y. So let's scroll back up real quick. We said x is beta alpha beta, and y is beta alpha beta plus gamma. So we also said they're independent, right? So this is just f marginal of x times the marginal of y. Marginal of x is a beta. X is marginally beta, so the PDF is that. In the basement, we have the beta function, which I just use b. It's x to the alpha minus 1, 1 minus x to the beta minus 1. And then for y, I have, again, beta, now alpha plus beta, gamma, and I have x to the alpha plus beta minus 1, 1 minus y to the gamma minus 1. And so that's the joint PDF of x and y, and then I need to plug in my inverse functions here. So what were my inverse functions? So what did we say? We said this thing here was 1 over v, g1 inverse is just v, and g2 inverse is u over v. I believe that's what we said. Is that right? Yep. That's right. So plug it in. F of uv is equal to, in place of x, we plug in v. V to the alpha minus 1, 1 minus v to the beta minus 1. And in the basement here, there's a beta alpha beta. And then in place of, whoops, this should be a y, shouldn't it? In place of y, we have u over v. So we have u of v to the alpha plus beta minus 1, 1 minus u of v to the gamma minus 1, and in the basement we still have beta of alpha plus beta gamma. So that's the answer. If I ask you, what is the joint distribution of x of u and v? And we're going to leave it there. You could get the marginal distribution, which is kind of an involved process, but if you wanted to get, I'll leave that maybe as an exercise, non-trivial exercise to you, right? So we had looked at x plus y, x times y, so you could actually get the marginal distribution of u, that would give you the distribution of xy, which would tell you if I take a beta alpha beta and a beta alpha beta plus gamma, or beta alpha plus beta gamma, multiply them, that's what it would give you. So this is kind of how, you'll see these formulas out there. For instance, if I take two betas in these form and I multiply them, it gives me this other distribution. It turns out in this case it's another beta. But that's basically how to derive, right? So I set one of the variables to one of the transformations to the one I want. The other one is something simple. I get the joint, and then I'll basically just integrate out v, and you can get the marginal of xy. We're not going to do that. It's kind of a little bit too involved. It's not bad. It's just a couple tricky integrals, but one could do it. The next theorem we want to talk about is what happens in the case where we don't have an invertible transformation. And this is basically a generalization of the theorem we saw in the univariate transformation case, where as long as we can break up the transformation into chunks that are invertible, we'll be okay. So let's look at the non-invertible transformation case. And I'm going to kind of skip over some of the details, but I'll say as long as we can break our transformation function g into chunks that are invertible, we're okay. So let us have A be the support, the bivariate support of x and y. So this is some subset of the real plane here. And A partitioned into a collection of sets of parts of the real plane, A sub k, and there's some capital K of these sets, and on A sub k, uv is equal to g1 k of xy, comma, g2 k of xy. All right, so here my function g1 superscript k is the g1 transformation function on the chunk ak, and g2 superscript k is the transformation function, the second coordinate transformation function on ak also. And so this is just kind of, it's a kind of cumbersome notation, but it's actually not so bad in practice. I guess we want to say, assume that the g's g1k and g2k are invertible. Then, not too surprisingly, like in the univariate case, if I want to write the joint PDF of u and v, I'm just going to take and apply the function, apply our theorem on the chunks and then sum them up. So basically, I'm going to say that a little bit cumbersome notation, but I'm going to take my joint PDF of x and y, and instead of x and y, I'm going to plug in G1 and G2k. This is supposed to be inverse at u and v, and I'll multiply by the determinant of the Jacobian, derivative of gk inverse with respect to u and v, absolute value of that, and then I'll sum it all up. But this is kind of the operative theorem here, and in practice it's not too hard, as long as you don't have too many chunks, but it's just basically applying the previous bivariate transformation theorem for this continuous case to the chunks and then summing them all up. So the theorem's a bit of a mouthful to write down here. Let's look at some examples. So here's our example. X and y are IID normal 0, 1. So they're both normal 0, 1, and they're independent. And let's say u is x over y, and v is absolute value of y. So this is not an invertible transformation because of this absolute value of y, right? Because absolute value function is not invertible. But if we look at the real plane, so this is kind of our real plane, you could break it up into two chunks. You could break it up into a chunk A1, where y is bigger than 0, and you could break it up into another chunk, basically the lower subplane, where y is less than 0. Because it continues, you don't really have to worry about the case where it's equal to 0. It's not going to matter in the long run. So if we want to derive the joint PDF of u and v, we just need to apply it to each of the two chunks. And on the chunks, this thing is going to be invertible. Notice that I've split it up based on whether y is bigger than 0 or less than 0, so that on each of those two chunks, this will give us an invertible function. So let's look at how to do this. We'll do it in detail on chunk 1, and then we'll kind of state the result for chunk 2 here, for A2, but it's very similar. Okay, so on A1, u is x over y, and v is absolute value of y, which is just y, right? Because if y is bigger than 0, absolute value of y is the same thing as y. All right, so our chunk A1 here is the set of points x and y such that y is bigger than 0. And so if u is x over y and v is y, then if we want the inverse functions, let's solve back for x and y. Clearly, y is v, and to solve back for x in terms of u and v, I can say that x is what uy is uv, so x is uv. And this basically gives me my inverse functions, g1 on chunk 1 inverse of uv is just uv, and g2 on chunk 1 inverse of uv is just v. The notation, yeah, not the greatest notation, but that's what it is. And so we want this Jacobian matrix, and so the first row is the derivative of g1 inverse with respect to u and v, which just gives me v or u. And the second row is the derivative of g2 on chunk 1 inverse with respect to u and v. Derivative with respect to u is 0, and v is 1. And so the absolute value of the determinant of this thing is, what? Just v. We can do a similar kind of thing on chunk A2. So we'll kind of hold it there for now. On chunk A2, I'm going to just say we can show, I mean, it's basically the same kind of deal, that G1 on chunk 2 inverse of UV is negative UV, and G2 on chunk 2 inverse of UV is negative V. So we get the negative sign because we're on chunk A2. A2 is the second set, which is points x and y, such that y is less than 0. And the absolute value of the determinant of the Jacobian in this case is also just going to be v. So it's the same, because of the absolute value sign, the Jacobian determinant is the same. So we get the inverse function, we get the derivative Jacobian for each of the two chunks, and then we combine the chunks. So fxy of xy, the joint PDF of x and y, we said, well, what did we say they were, right? Let's go back up. We said that x and y are standard normal, IID standard normal. So that's pretty straightforward to get. The marginal of x is just the marginal of x times the marginal of y. Marginal of x looks like this, and the marginal of y correspondingly looks like that. And so the joint PDF of u and v, there's going to be two things we're going to summing up because we have the two chunks, right? So we have to sum up the part on A1 and the part on A2. And, let me write it out. So it's fx, it's the joint PDF of x and y, evaluated at G1 on chunk 1 inverse of uv, and G2 on chunk 1 inverse of uv. And then we multiply by the Jacobian determinant, which is v. And then we add on the part for chunk 2 of x and y, which is G1 on chunk 2 inverse of uv, G2 on chunk 2 inverse of uv. And we also multiply by v because that's the Jacobian determinant. And then we'll just plug in for what everything is. So 1 over root 2 pi e to the negative 1/2. This is what we're replacing with x, and that is u times v. So instead of x, we get uv quantity squared. And then we have another 1 over 2 pi e to the negative 1/2. Instead of y, we're going to put this thing, which we said was just v, so v squared, right? And, okay, and then we add on, oops, don't forget our Jacobian determinant, which is this v, that comes down. Then we add on the corresponding part for chunk 2. In this case, it's negative uv squared. And then we have the second part, which is negative 1/2, and it is negative v squared. And then we multiply by v again. You notice there's a lot of stuff that's repeated here, right? So we're actually going to be able to simplify this thing quite a bit. So let's just see how much we can simplify here. Oh boy. Certainly we can combine the root 2 pi's to just 1 over 2 pi. And then we get e to the negative 1/2. And we can sum up all the exponents, right? Which is what? U squared v squared plus v squared, but we actually have that for both the exponents, right? So we have that here, and we have that here, and we have that kind of repeated again. So what we actually get is 2 times u squared v squared plus v squared. So I think that should be the right exponent for that. And we have a v. You know what? That's not how you sum exponents. Let's back up there. Oh boy, trying to combine two of these steps at once, right? The 2 cancels here, right? There should be a 2 here, which cancels, right? This is just going to be u squared v squared plus b squared, right? And I sum. These two sides are identical, right? These two sides are identical. And of course we have the v. Just algebra. So nothing too complicated, just some algebra. So what I think you get at the end of the day, if I've done my algebra correctly, is, well, let's write it like this. V, which is the Jacobian determinant, 1 over pi, and we have in our exponent an exponential of, we have a negative 1/2, and then we could say v squared times 1 plus u squared. Okay, so that is, we actually do the algebra correct, right? If I just ask you for what the joint PDF is, you could always stop at this step, but you could simplify it down to this. And again, the reason, so we'll pause there and say, okay, that would be a reasonable solution to this problem. The reason is, let's say, what about the marginal of u, right? What if I want to have the marginal of u? U was x over y. Why would I want that, right? So if we go back up to the beginning of our problem, we have x and y are standard normal, and u is x over y. So interesting question is, what's the distribution of the ratio of two standard normal random variables? We know that the joint of u and v, which is the ratio and the absolute value of y, has this thing as its joint PDF. And if I want to get the marginal of u, of course, I can get the marginal of u by taking the marginal of u and v and integrating out v. So if we just integrate out v, in this case, v is absolute value of y. It can go anywhere from 0 to infinity. And so what I'm integrating out is, it's b over pi e to the negative 1/2 v squared times 1 plus u squared, right? It's back to v. And so this is kind of a nice little Calc 2 problem. If I simplify things, so first of all, let's just call beta 1 plus u squared. U is not what we're integrating against. In that case, certainly I can pull out the 1 over pi out of my integral. I'll be left with the integral of v e to the negative 1/2 v squared dv. Now this is a classic u substitution problem. So let us say, well, let's not use the letter u, let's say w is, what do we want to make it? 1/2 v squared. Then dw is v dv, and this integral here, the 1 over pi, the integral, whoops, I forgot my beta here, right? There should be a beta on this, right? That's just my 1 plus u squared. In that case, what's my integral? It's the integral. Maybe I should change my u substitution, right? I should have a beta here. Let's add the beta to my u substitution. There we go. Okay. If I do that, now what's my integral? What are my limits, right? My limits should still be 0 to infinity, right? And then v dv is the same thing as 1 over beta. And there should be a dw, right? So v dv is dw over beta, and then my integral here, it's just a u substitution problem, is negative 1/2, whoops, not even negative, and then this thing was just w, right? That beta doesn't depend on w, so 1 over pi beta, integral 0 to infinity, e to the negative w dw. And you have to believe that that thing is going to give me 1, right? So all I'm left with is 1 over pi beta. But, of course, beta was 1 plus u, right? Ultimately, what I'm trying to get is my marginal of u. And so I get 1 over pi times 1 over 1 plus u squared. So that is my marginal PDF of u. And this, if you may recall, is called a Cauchy distribution. We ran across this with expected value because Cauchy random variables do not have a expected value or a variance, that the integral doesn't actually converge. So it turns out that that Cauchy random variable, which kind of was a weird random variable that didn't have a mean, didn't have a variance, and kind of the improper integral didn't converge in the right way, turns out it actually arises as the ratio of two standard normals, right? So remember that u was our ratio of two standard normals, and if we do that, we get that u marginally as a Cauchy distribution. So again, this trick of this problem, and there's a good example A of getting a marginal distribution, some review of some u substitution. It was a nice example of our a non-invertible transformation, how to apply that. But it's a really classic trick again, right? So if I have x and y as standard normal, and I say, well, I want to know what the distribution of the ratio is. Well, I can pick the ratio, and then I pick something else clever to make my problem easy. I get the joint of u and v, and then I say, well, let's just get the marginal of u, and I integrate out v. So that's a real classic trick to do. Let's do one more example today. One more bivariate transformation example today. And this is just going to be an invertible classic bivariate transformation, just for some more practice. So here's my example. I'm going to say x has a gamma distribution with parameters alpha, lambda, and y also has a gamma distribution with parameters beta, lambda. And I'm going to say x is independent of y. And I'm going to look at, consider the bivariate transformation, u, which is x plus y, and, and v, which is x over x plus y. Okay. So u is the sum of two independent gamma with the same second parameter. And b is kind of this ratio, right? So x over x plus y should be some number probably between 0 and 1, right? So what distributions do we know are distributed between 0 and 1? Could be uniform, could be beta. Yeah, so maybe it's beta. Well, we can actually figure this out and figure out what's going on. And this is another kind of classic transformation problem. So step 1 is get the inverse transformation, right? So u is x plus y, and v is x over x plus y, which is x over u. And this implies that x is uv. Well, there's one of the inverses. That was g1 inverse of u and v. That gives us x is u times v. And so using this second part, I can then say that if x is u times v, then u is uv plus y. So y is u times 1 minus v. And that gives me my second inverse transformation, my second coordinate. This is g2 inverse of u and v. So those are the inverse coordinate transformations. And we need the Jacobian, right? So we want j. And okay, so the first row is the derivative of g1 inverse with respect to u and v, which is just v and then u. So derivative of uv with respect to u is v, and respect to v is u. Derivative with respect of u times 1 minus v with respect to u is 1 minus v, and respect to v is, what does it give us, negative u? Yep, that makes sense. And what this implies is the absolute value of the determinant of my Jacobian matrix is Well, it is absolute value of negative uv minus u times 1 minus v, which actually turns out to just be u. I can drop the absolute value bars because both u and v are always positive, and that actually, yeah, negative uv minus u plus uv, which leaves me with just u. So step 2 here is plug in to joint of x and y. All right, we basically have all the parts. The parts being, we wanted this Jacobian determinant. We wanted the coordinate inverse functions, that one and that one. And we said that x and y are independent. So again, super nicely, this joint distribution of x and y, joint PDF of x and y, is just the product of the marginals. And we said that x was gamma alpha lambda and y was gamma, what did we say, beta lambda, right? Oh, so you have to remember the gamma distribution. So the marginal of x is lambda to the alpha, x to the alpha minus 1, e to the negative lambda x, all over gamma of alpha. And similarly for y, it's lambda to the beta, y to the beta minus 1, e to the negative lambda y, all over gamma of beta. And so to get f of uv, this is f of x, y. Our inverse functions are what? Our inverse functions are, well, let's scroll back up and look at them. Inverse of x is uv, so we plug in uv. And inverse of y is u times 1 minus v, u times 1 minus v. And the Jacobian determinant was just u. That gives us just u. And plugging them in, this gives us lambda to the alpha, uv to the alpha minus 1, e to the negative lambda uv, gamma of alpha in the basement. And then instead of y, we plug, not y, we plug u times 1 minus v to the beta minus 1, e to the negative u times 1 minus v times lambda, all over gamma of beta. Okay, so that is the joint PDF of u and v. But again, there's going to be some algebra. And I'm not going to do all the tedious algebra, but you can basically collect together some terms, collect the lambdas, lambda of alpha plus beta, and I can collect the gamma of alpha and the gamma of beta, right? None of those terms depend on u and v. And if I collect all the powers of u, what I'll be left with is u to the alpha plus beta minus 1. So there's a u here, and there's a u there. And I'll be left with an e to the negative lambda u, right? If I combine these. So there's a little bit of algebra you have to show. And then if I collect all the powers of v, so this is not directly, there's some algebra here, right? If I collect the powers of v, I'll have v to the, I'm forgetting my u here, that's where that comes from, right? This is my u, combine those, alpha beta plus minus 1, e to the negative lambda u. My v powers, I just have this one here, is v to the alpha minus 1, and the other part of my exponent that's going to be left over is, oh, well, actually all of my exponent, if I combine this and this, I'm just going to get e to the negative lambda u. What I'll also be left over with here, let's do this in a different color, just so I have v to the alpha minus 1. I'll get a 1 minus v from this part to the beta minus 1. So these might look kind of familiar. This is, say, proportional to the PDF of a gamma alpha plus beta lambda. And this is proportional to the PDF of a beta distribution with parameters alpha and beta. So go back and look at what those PDFs look like. Those are basically proportional to them. And notice that this first thing only depends on u. Only depends on u. And the second thing only depends on v. So the kind of final result here is that u is independent of v. Why can I say that? Because I can factor what is the joint PDF into a function of only u and a function of only v. And furthermore, because the part involving only u is proportional to a PDF of this gamma, we know that u must have a gamma alpha plus beta lambda, right? It's going to have to be that. And because v is proportional, you basically have to show that the product of the constants of these things gives us this blue part out front. Because the PDF of the part only involving v is proportional to a beta distribution with parameters alpha beta, it will be distributed as that beta distribution. And so what we've shown is that if we go back up to what the actual problem was, we had x was gamma alpha lambda, y was gamma beta lambda, x is independent of y. If you sum them together, or if you take the ratio of x over x plus y, the sum, that is u, is here, which is x plus y, is another gamma. So if I sum gammas with the same rate parameter lambda, I can just sum their first parameter. And furthermore, if I look at x over x plus y, that will be a beta distribution. Which makes sense. X over x plus y should be between 0 and 1. And it's not too surprising that a beta distribution, which is between 0 and 1, is distributed that way. So let's stop there.